Okay, everyone. I decided to split this up into another video. So this video is going to be hopefully short, and we're going to talk about the various variations that you have in how you can set up this Q-learning algorithm that we went through before. So variations in how you calculate alpha, the learning rate, and variations in how you handle the exploration probability. And I'm just going to skim through these, but I do want you to see them. There are more details in the reading. All right, so the most simple thing to do with alpha is just to fix the learning rate and don't ever change it. Just set it to something. And the code that you'll work with in the activity does exactly that. It just sets it to a constant value and leaves it alone. Now, you could change it over time. So you could set the learning rate to be high initially because we want to learn a lot when we don't know anything at all. And then we could gradually just decrease it on a fixed schedule. That should sound familiar. It's a little bit like the simulated annealing that we looked at in terms of like the local search that we did earlier. So we could just have alpha diminish over time. What is often more common, and this is the pseudocode that's in the textbook, is to compute alpha based on the frequency with which the current scenario has been seen, which is like the more we have been in a particular state and chosen a particular action, we could assume that we know better what's going on in that situation. Whereas if we are in a state and we've never chosen a particular action, we might want to learn more because we just this is our first time experiencing it. So there are various formulas that you can use that update alpha dynamically based on the exact situation that it's finding itself in. And that we'll do a look at that in the activity as well. All right, so there are more variations in terms of choosing whether to explore or exploit. So I'm going to look at a bunch of these that go from really simple to much, much, much more complex. And they're just good things to have in mind. So you could have the exploration probability fixed. In the code that you're going to work with in the activity, we do fix it initially. My initial code just has it set at 0.2 and it does nothing else. And that's not the greatest, as you will see. So one of the things you'll be doing is making it at least a little bit more elaborate. It is really common. This is probably the second option here is probably the most common approach, which is to have the exploration probability decrease gradually over time. There are variations like when does it stop? Do you just let it decrease forever? And what happens when it becomes negative? Would you have it go to 0 and stop? Or maybe you want to stop it with some small probability that it still does an exploration step. All of those are perfectly good options. You just need to try one and see what you like. There are some more elaborate ways of handling exploration versus exploitation. So one of them is based on thinking about a row of the table in a softmax term. So you take those values, those reward values in the table, and you scale them so that they are all between 0 and 1, and they add up to 1. Not super difficult to do, but you need to do it. And then you can use it's a Gibbs or Boltzmann distribution. It relates to simulated annealing again, because there's a temperature in here. And the probability of selecting action A in state S is proportional to this nice little friendly formula here. E to the power of the old value divided by the temperature. That's just an option. It's in your readings. And again, the nice thing is that it's somewhat relates to, how do I want to put this? If you had a row of the table where there was fairly good rewards across many actions, maybe you want to explore there. Whereas if you have a table where there are lots of bad choices and one really good choice, maybe you would want to treat it differently. So this does a little bit of that because it relates to the probability of the distribution across all of the actions. There is also this upper confidence bound method that is mentioned in your readings. So basically, we do this formula to calculate how confident we are in the correctness of our predicted value. So we take the old value, we multiply by a constant C that you have to set. And then in here, we're looking at dividing the overall times we've been in this state by the number of times we've been in this state and chosen this action as a way of scaling what we want to do. So then what you would do is choose the action that has the highest UCB score. And the score then incorporates both exploitation and exploration as a part of it. All right, so those are just some simple variations. We'll take a look at some of these in our activity. Just know that there are lots of ways that you can implement Q learning that can be different depending on the specifics of your task.